Welcome back, everybody. We'll pick up where we left off. As a reminder, so I moved the due date of the homework for 0.4 until this Sunday. You'll be able to do everything, like you were able to do most of everything on there except for like the last 3 or 4 topics. But now today we'll be able to finish it all and it'll be all done. So try and get it done early. The quiz for that week for last week has been extended till this Wednesday because the fact that we didn't finish this and there are questions in the quiz that deal with foiling. So we'll be dealing with that. And then we'll move on into factoring. So to rehash what we did last time, we were asking ourselves, how do we go about multiplying two binomial things together? And what we realized was that it was just distribution 2 times. So when we distributed the A comp like this as a whole term into it, and then we distributed the C in and the D in separately. And what we noticed is that both like A got applied, A is combined with C and with D, and the same thing's true with with B going into C and D. So that's what we call the FOIL method: first, outer, inner, last. So you do the first terms together, the first terms of each binomial, then the outer terms, the ones on the outside, then the inner terms, the ones on the inside of the multiplication, and then the last terms, the last term in the first binomial times the last term in the second binomial. And that's what it's called, foiling. However, really what's happening, and the way I usually like to present it, so I drew it like that, but we were doing that hastily. And the way I typically draw it myself is basically what's happening. Instead of thinking of it as foiling, this first, outer, inner, last, it's that each term is getting applied. Each term from the first set is getting applied to the second set. And the reason why I like thinking of it that way is that makes it more generalized. This means I can expand this to trinomials, or 3-term binomials, to 5-term, to 80 million term, whatever I want to do to be generalized. So each term of the first set has to be distributed into each term of the second set. And so let's go ahead and work through that. So you've got 3x minus 2 times x plus 4. So once again, each time the first term is going to get distributed and the second term is going to get distributed. So from the blue, and maybe I'm going to color code it this first couple times, but if you feel comfortable skipping that step, I encourage you to do so. And if you don't even want to draw the arrows, that's something you get to over time. Once you feel comfortable with it, you can stop drawing those arrows. It's a good checking and balancing thing when you start off, though. And I still do it when I'm dealing with very, very large polynomial multiplication. So the 3x times the x would be 3x squared. The 3x times the 4 would be a 12x. The negative 2 times the x would give me a minus 2x. And then the negative 2 times the 4 would give me a minus 8. Oh, I wanted to change those to be in purple. And from here, we're not finished. We're close, but we're not finished because there are some like terms in the center. Whenever you do a foiling of two binomials, you'll always find, if they're all single variable, if it's all the same variable, you'll always find like the inner terms should kind of match up and combine a little bit. Sometimes, well, not necessarily. I'm just forget I said that. So combining those two inner terms, that'll be plus 10x minus 8. This next one, part B, notice that there is a minus sign out front, which is a negative sign that will have to get applied. And there are a myriad of ways we can do this because, yes, this is a binomial times a binomial with that additional -1 out front. But at the end of the day, it's all multiplication. At the end of the day, it's all multiplication. So we can do it however we want. Remember, the associative property says that we can multiply the first two together first if we want to, or the second two together first if we want to. It doesn't really matter which ones we do. So we could, if we so chose, we could distribute the minus sign into the first set first and then foil, or we could take care of the foiling, take care of the distribution first, then take care of the minus sign. Convention would be to do the binomial multiplication first, but that's just me. If you want to distribute the minus sign in first, go right ahead. But I'm going to do it by this method. Distribute it in. Distribute that in. And so we've got that negative sign. Don't forget about it. But then on the inside of these parentheses, 5 times x squared is 5x squared. 5 times 1 is plus 5. Negative 4x times x cubed would be negative 4x, or sorry, negative 4x times x squared would be negative 4x cubed, i.e. negative 4 to the times x to the third power, and then minus 4x. So, unlike the first situation, we call these things, these would be linear factors in part A. Those are linear factors because all the variables are only being raised to the first power. Whereas with the second set, part B, the first term is a linear term, but the second term is what we call a quadratic term. We'll get to that in a second. And so when we look at the foiling process, when we've written it out, there's no like terms. None of things can be combined because they're all to different powers of x. And typically speaking, we like to see our polynomials in descending order or ascending for very, very niche situations. But for the most part, descending order. So that 4x cubed should come first, then the 5x squared, then the minus 4x, then the 5. But at the same time, I can, well, let's rearrange it first and then distribute. That negative sign, and then it's going to be negative 4x cubed plus 5x squared minus 4x plus 5. And so now I'll distribute that minus sign into all the things, giving my final answer, which will be a positive 4x cubed minus 5x squared plus 4x minus 5. Because the negative sign will change all the signs. It'll flip them all. The positives will become negatives and the negatives will become positives. But I encourage you, if you want to, try it a different way. Try to distribute the minus sign. Oh, though, be careful. Be careful. I'm going to write this down. Just don't bother writing this. Just observe. Because this might be something that you'd be interested in trying, but it doesn't work. Some students would like to try and do this. They'd say, okay, well, I'll distribute it in. That doesn't work because that would be multiplying it into two different terms. Because this is like, that would be multiplying it into this and then also again, but that doesn't work. So it would need to go only into one set because treating it like multiplication, this would be multiplying it into two things at once, which we don't do. Does that make sense? It's okay if it doesn't, please feel free to ask. All right, I'd like you guys to do part C, and then part E will come together. And then part F we'll talk about together. Every time. Just slowly fill in details. I have the answer up here if you'd like to check your work. So, you'll FOIL it out. You'll distribute them in. You'll get a 64x squared plus a 6xy minus, or sorry, 16xy minus a 16yx plus a 4y squared. Yes.
Should be negative or minus 4y squared.
You are absolutely right. You are absolutely right. Thank you. Good catch. It should be a minus 4y squared. Thank you. Good job. Just making sure to test you guys. Sure to make sure you guys are on your toes. So thing is, remember that the 16xy is the same thing. The 16yx is the same thing as 16xy by the commutativity of multiplication, right? We can jumble the terms around however we see fit. So the inner two terms are like terms, and they in fact cancel out completely. And that's a really cool thing, by the way. This is a very common trick, and we're going to learn about what this is when we talk about factoring. But 8x minus 2y and 8x plus 2y, those are what we call conjugates. They're conjugate terms because they have the exact same stuff, but the only thing that's different is the sign in the middle. There's a big reason why we study conjugate. We call this process conjugation, and conjugation is very, very useful. In Math 181, you'll use it to simplify some limits. In later math courses, you utilize it a lot to simplify or to work with new concepts. I know you do a lot of it in linear algebra, maybe upper division linear algebra, but either way. So it is a process. It's one of those little tricks. It's one of those tools in the tool belt that we utilize. And especially becomes useful if you have to solve radical equations, so you don't have to spend a lot of time. Yes.
So how come like in this answer, we don't factor out like a 2, but other times it's like, factor everything out?
Excellent question. So like we could factor out a 4 here. Yes, we could rewrite this like, are you saying right now writing this as
How come that answer is right? Like, look at another future problem. I don't know how to explain it.
No, I see. I believe I know exactly what you're saying. Like, why is right now that an acceptable answer, but later on it won't be? And it's because of the context. Here we're asking to simplify, to write it out in all terms. But later on in the next unit, we're going to talk about factoring stuff. And factoring is going to be doing the undoing of this process. And that's when we want to bring things out. If you've looked at like I know photomath and things like that, they'll want you to start factoring crazy and stuff. And that's just because of the programming is kind of weird. But for us right now, we don't need to worry about simplifying or like factoring things out because that's not what we're focused on. We're focused on how to break it down into the small pieces without factors. So right now we're breaking it down into its pieces. We're combining it into little elements. Later on, we're going to take all the big elements and break them down. So it has to do with whether or not we're factoring or simplifying. This next one is much like the first one. There is a lot part B where we have to worry about that multiplying by 4. And in that case, we can either distribute it in first or distribute it in later. It's your call. I'm going to wait until the end. So I'm going to FOIL this in. There, and there, and there. So don't forget about your 4, but 1/6 y times 6x, the 6ths cancel. The 6th cancels with the regular 6. So the first term is just an xy plus. Now you can either do it all in your head or on your calculator, doing 9 times 1/6. You can do that, or you can leave it unsimplified at first and deal with it later. It's your call. I'm going to deal with the simplification. Since I know I'm going to have to distribute the 4 in already anyways, might as well just take it slow, but it's okay to simplify earlier. So I get 9/6 y, and that's taking care of all of the pink distribution. Then we got to do the green distribution, so plus 12x plus 18. So now that I've written it down, I'm going to reduce that 9/6 because there's a common factor of 3. Canceling the 3 in the numerator would leave me with a 3 because 9 is 3 times 3. And canceling the 3 in the denominator would give me just a 2. So really, it's 3/2 y. Any questions so far? Then we'll distribute. Boom, 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 boom. And 4xy will just be 4xy. When we distribute it in, remember, you can use your calculator, but when you distribute it into the second term, the 4 and the 2 will cancel slightly, getting rid of the fraction, and we'll have a 2 left over, so it'll be 6y. And I'm happy to show that work if you'd like to see it, just ask. And then 4 times 12, that's 48x. And then 18 times 4, that's 40 plus 32, which is 72. Right? Excellent. I can do my arithmetic. Which I'm gonna need this anyways for my next class, so I'll put it out. And that is our final answer. Any questions on that one?
I actually have a question on the last one.
Yes.
Where it's negative 16yx. If we were to put it on our answer, like if it was negative 17yx, and we wrote the answer as negative xy, would we be wrong?
Nope.
Like
So-
having the answer matter?
So if it had been like this, so if it had 16xy minus 17yx,
Yeah.
and if you wrote negative yx like that,
If we wrote negative xy,
excellent question. So JTS is a perfectly valid question. 16xy minus 17yx. Should the answer be negative yx or negative xy? Answer is it shouldn't matter. It shouldn't matter. Convention would be to put to go in alphabetical order, right? So we should put the x's first just by convention, but it's not wrong to write it as yx. It's like saying ATM machine, right? Because ATM is an auto transaction machine. So like saying an ATM machine would be auto transaction machine. So like it's technically wrong, but nobody really cares. So, all right. Now we come to one of the biggest mistakes that students make in algebra. So, classic mistake that students will make on this problem, and I don't want you to write this down, is they will do this. They'll say, okay, well, I'll just distribute this exponent. And so I get 25x squared minus 9, because 3 squared is 9. That is not correct. And the reason for that is we have to remember what exponents do. An exponent means, by definition, it means multiply it twice here. So this is the same as 5x minus 3 times 5x minus 3. So you have to FOIL, you have to distribute. So students will want to do that, and I understand why, and that's why I've got this important aside. Let's finish this problem, and then we'll talk about it. So then we just got to FOIL. Let's use blue. And when we do this, the 5x times the 5x will give me a 25x squared. The 5 times the negative 3 gives me a negative 15x. The negative 3 times the 5x will give me another negative 15x. And then the negative 3 times the negative 3 will give me a positive 9, because a negative times the negative is a positive. And those negative 15x's don't cancel because they have the same sign. Do you remember about that? Yes, I'm aware that my Apple Pencil is low on battery. If it was negative 15x plus 15x, then they cancel. But here they're going to combine. They're going to double in size to give us our final answer, which will be 25x squared minus 30x plus 9. So if you had done the illegal math, if you'd done it incorrectly, you'd be missing a whole negative 30x. Because like when you saw the red, I had written 25x squared plus minus 9. So not only was I off by a sign on my constant term, but I was also completely missing that inner term because I did quote unquote illegal math. And so the thing is, we cannot distribute exponents over addition and subtraction. We learned way back last week, I know it seems ancient ago, we learned property 4, where if you have multiplication or division and then an exponent, you can distribute the exponent in. But that's because what you're doing is you're taking multiplication and iterating multiplication, because that's what exponents do. They're a way to write out multiple multiplications. So that's why it can be distributed into the multiplication, because all you're doing there is just a huge string of multiplications. In contrast, x squared plus y to the fifth squared, there's that plus in the middle of it. So what you're really doing is you have two terms that you're multiplying. They're not combined with multiplication. So you have to distribute. So with the legal math, the answer would be correct, which you do, since this is multiplication. You can write this then as x to the 2 times 2, which is x to the fourth power, times y to the 5 times 2, which is y to the 10th power. Remember, if you have a power raised to a power, you multiply the powers. It's not 2 plus 2 here, it's 2 times 2, which just so happens to be the same number, but that's a common mistake that students make because it's like it happens so often that we just think that it's adding. It's when you have power raised to a power, you multiply. Now, the illegal math would be to try and just make this. So I'm going to write this in red and say this is, then this would become x to the fourth plus y to the 10th. This is not true. This actually has a name, by the way. If you look it up, if you search in Google the freshman's dream, quote unquote, this will show up because it seems like it would be so nice if it was true, right? It'd be so nice if we could just do that and not have to FOIL, not have to distribute, not have to rewrite it. But sadly, math isn't always nice and neat. A lot of times it is, but sadly here it's not. So to sum up, we cannot if blank plus or minus blank to a power need to distribute. You have to distribute, otherwise it's not valid math. So every single time a student does that, by the way, a mathematician loses 1 year off their life. It's a true story. So every single time you do a freshman's dream, I will lose an extra year off my life. Now, I mean, granted, don't want to be here much longer anyways, right? It's a dark joke. Way too dark of a joke, way too dark. I'll dial it back. I'll dial it back on that front. But I don't want my colleagues losing years off their life, okay, guys? So please don't. Well, maybe some. I'm terrible. Okay. I'm kidding. I'm totally kidding. I love all my colleagues. Okay. I'm getting way too sidetracked. I forgot what that note was supposed to say. What was it supposed to say? Well, I'm sure if it's important, I'll remember it. Otherwise, just say woot. Okay. So let's go ahead and do these ones here. I want you guys to do A and B. I'll slowly fill in details. So when you get really skilled at doing foiling, and you've got to have you've got square like second powers and stuff, you can sometimes notice the pattern and skip the practice and just write it down. But I highly recommend when you're starting out, writing out what the exponentiation does. So meaning 2x minus 3 times 2x minus 3, write that step out when you're starting out. If you take enough math courses, I don't know how many of you guys write your Z's just as a kind of looking like a two. But if you go long enough into mathematics, you have to start writing your Z's with a line in the middle. You'll thank yourself later. I did like before I got into math 283 here. I took it at UW, it was math 126, but either way, multivariable calculus, you start dealing with X, Y's, and Z's. And so it was then that I had to start dealing with writing it because otherwise it started to look like twos and I would get things wrong. A couple things that have changed because of that. Not supposed to say Z, it's 14X. Or 14Z. Yeah, 180, 120. 147, yes. Good. All right, so you should get for the first one, you should get 4x squared minus 12xy plus 9y squared. And then similarly, or not similarly, but for part B, you should get 3z cubed plus 42z squared plus 147z. So for the first one, by the way, so I wrote it again where like when you distribute it technically for the third term, you get a negative 6yx. But from now on, I'm going to skip writing that. I'm just going to write them in the same order all the time because of the commutativity of multiplication. It means the same thing forwards and backwards. So you combine those things to get negative 12xy plus the 9y squared. With the second one, I wanted to rewrite this like a common thing that some students might want to do is when they see that 3z, z plus 7 squared, they might want to try and distribute in the 3z. But we actually talked about this in a previous example, and the fact that because the 3z is not raised to the second power, we can't distribute it in. You can only do that if they're all being raised to the same power. And you can see that if I were to do that, then I'd get 3z squared plus 21z squared, which by definition would be 3z squared plus 21z times 3z squared minus plus 21z. And now 3z got applied twice. That's why we cannot do that. Instead, it's just better to take care of the foiling first. Not wrong to do so, but it definitely, you need to be careful. That's why I decided to write it out to remind myself that I can only distribute this into one factor, one set. Okay. Any questions on that? Now with this next one, part C. So I have a binomial times a trinomial. And with that in mind, if you think about foiling, then there's no, like, it's not going to be first, outer, inner, last. There's a middle term too. So like, how do I deal with foiling? That's why I don't really like to use the terminology foiling and instead understand it as distributing each term in the first set into each term in the second set. So the way I would write it would be I'd be drawing this and saying, okay, the 2x is going to get distributed into each of the three terms of the trinomial, and similarly for the 5. Now that's the way I'm going to do it, but there's nothing stopping us, remember, because multiplication is commutative. You could also just as easily say, well, I'm going to distribute the x squared into those two terms, then the 3x into those two terms, and then the 7 into those two terms again. It looks a little more confusing that way, but just showing you that you can do it in either direction. It doesn't matter which one you choose, so long as you stick with it. But I prefer doing less arrows if I can. It becomes a little less messy this way. No, this is not. So distributing in the blue distribution will give me 2x cubed minus 6x squared plus 14x. And then the green distribution will give me plus 5x squared minus 15x plus 35. And then there's going to be some like terms that can be combined. X cubed has nothing in common. The x squareds have some stuff in common, and the x terms, but the constant terms don't. So at the end of the day, we should get 2x cubed minus x squared minus x plus 35. All right. And these last two are some bigger ones, but we can work through them. I'd like to do D together, and then I want you guys to try E yourself. Unless there's any questions on part C. I'm very excited that we get to do, we're starting factoring today. Factoring is a very, very fun thing for me. Kind of like Sudokus. There's always an answer. It's always fun stuff. So 2x plus 1 cubed. For the same reason as before, we can't distribute the cube in because it's not a product of things. It's a sum of two things. So we have to worry about distribution. By definition, this is 2x plus 1 times 2x plus 1 times 2x plus 1. I'm going to shut down the program and restart it. It's starting to lag. Two x plus 1 multiplying into itself 3 times. So when we do that, you could either multiply the first two together or the second set together. Or you could, if you really wanted to go bonkers, you could multiply the first and the last set together. I don't know why you would, but you could. Just so that like it will be easier legibly to multiply the last two together. So we get a binomial times a trinomial. But just because that's not necessarily what we're thinking in the heat of the moment on a quiz or an exam, let's just go straight forward, left to right. So we'll do the first set, and it's going to be okay. So we'll distribute that in. You're going to get 4x squared plus 2x plus 2x plus 1. And that's going to be multiplied into that 2x plus 1. Make sure you see where I got everything. And if you have questions, please feel free to ask. Because this is actually a good thing to talk about when it comes to, well, no, never mind. We'll get to that later. So we could go right now and FOIL. We could, or distribute. We could do that. However, we'd be making more work on ourselves because right now the first term is a quadnomial. It's a 4-term thing. And then that would mean I have to distribute 4 things in. But since there's like terms, we can combine those and make it a little bit easier on ourselves. So that's what we should do. We're going to rewrite this as parentheses 4x squared plus 4x plus 1 times 2x plus 1. And then we've got to distribute. So we'll take the first one, distribute it into the set. Second one into the set. And then the third one into the set. Sometimes I draw like a little bit over like big humps to make sure it doesn't get confused with the other ones. And foiling that out, we should get 4x squared times 2x. That's going to give me 8x cubed plus 4x squared. Then the blues, I'll get plus 8x squared plus 4x. And then the greens, I'll get plus 2x plus 1. Combining like terms here, there's a couple common factors of like there's x squared like terms, there's x like terms, but there's no x cubed like terms, and there's no constant like terms. So combining it together, we get 8x cubed plus 12x squared plus 6x plus 1. We could, I'd love to talk about Pascal's triangle, if you've ever heard of it. Pascal was a famous mathematician, and he noticed a pattern that starts to evolve when you start raising things to higher and higher powers. If you keep doing the same, like if you keep raising the same thing to higher and higher powers, you notice a pattern in the coefficients. And it's really, really cool. And it looks like this. This is what Pascal's triangle looks like. Do you notice any patterns that like how is the next row going to look? Pattern recognition. You see what's happening? One plus two is three. One plus three is four. Three plus three is six, and so on and so forth. It just so happens that this works out. It actually, so this is if you were to do x plus one squared. These would be the coefficients. But you'll notice this is divisible by three, so is this. And it's because there's going to be some cool stuff going on. I don't have time to go into it. I wish I could. If you want to know more about Pascal's triangle, it's just a fascinating little math fun thing. But either way, please feel free to talk to me, and I'm happy to talk your ear off about it. So that's our final answer. This last one, so all for the whole kit and caboodle, we have to do a trinomial times a trinomial. If you can do this, you've got the concept down. If you can do this, you understand how to do the quote unquote Foilinger distribution. So take it slow. It's okay. I'll slow fill in details. Especially take it slow because these things can, once again, there's a lot of terms. There's a lot of things being multiplied. And even I make mistakes on these things from time to time because it's a lot of things to keep straight in your head. I'm going to color code it this time, actually. Suspension. Keep working through it. Keep working. Check your work when possible. Make sure that I did it correctly. Because I can still mess up. Every morning for breakfast, I always make my wife and I some eggs on toast, and I still screw up the eggs from time to time. I'm not perfect. It's stainless steel, and if you ever use a stainless steel pan, it's a BZ and a half to make sure it doesn't stick. But especially if a person's demanding that you play Legos with them while you're trying to cook. You should get 5b to the fourth minus 7b cubed minus 19b squared plus 13b plus 8. Does everyone else get that same answer? Excellent. I did it right. I know how to do math. Any questions on distribution? Okay. I'll keep it up here if you like if people are still jotting down the last minute results. But is it okay if I move on to 0.5? Some people still writing, so wait. We're doing good on time. Because factoring is a big section. It's that's why we got 2 days. I think if you're looking at the calendar, do I have 3 days, like 2.5 days allocated to it? I think I do. No, I don't. But the good news is, by the way, so we're doing factoring for the next 2 days, and then the next 2 days after that, we're doing polynomial equations. But polynomial equations require factorization. So you're going to get plenty of factoring practice. It's going to be essential to all courses moving forward in mathematics. So I'm going to go to the next one. So factoring. So the way to start off with factoring is to talk about GCF factoring. So as we saw with the distributive rule, we were able to simplify expressions by taking the terms and going through them all, right? So take the 3x squared cubed, distribute it in, and you end up with, through distribution, you'll get 15x to the fifth plus 6x to the fourth minus 27x cubed, right? Yeah. So our goal now is to go backwards, to be given a polynomial in what we call standard form, in expanded form, and go backwards and get it into factored form. So our goal is to go backwards, factoring. That is what our goal for today and tomorrow will be, is to how to take a polynomial and break it up into small bite-sized pieces. Now, you might be wondering, why? Why would I want to do that? And that's an excellent question. When we get to unit 2, we're going to be talking about polynomial functions. And one of the things we study when it comes to polynomials is where they equal 0. And we'll get to that soon enough. We'll talk about polynomial equations. And factoring is the only way to solve non-linear equations. We learned how to solve linear, right? 4x plus 5 equals 9. We learned how to solve that. But how do you solve 5x to the fifth plus 6x to the fourth minus 27x cubed equals 0? That's going to require factoring. So that's why we're going to get to that, why we're doing this. So first definition. The greatest common factor or colloquially GCF, because I don't want to write greatest common factor. I'm definitely going to get carpal tunnel soon enough as it is. I don't want to keep writing out greatest common factor. It takes way too long. But the GCF, greatest common factor of a polynomial, is the largest factor that divides each term nicely. Meaning that when you put it over it, all the stuff in the denominator will cancel. So that's the way the way it works. It's the largest small thing. So the least common multiple was the smallest big thing that went in, that they all went into. This is the reverse concept. This is the largest small thing that goes into all the terms. So for the polynomial 6x cubed minus 9x squared plus 18x, the GCF equals 3x. Now, as you start off with it, you might be wondering, well, how did you figure that out? Why? And when you're starting out, it's best to look at the trick when starting out is to look at each term, look at each, find the GCF of each part separately. Find the GCF of each part of all the terms separately. So find the number portion, then the X portion. If there's more variables, find that one next, and so on and so forth. I got some examples down below. This is what I usually do when I'm starting out. So I'll list all the terms, and I'll kind of break them up into columns. So 6x cubed. Then we have negative 9x squared. And then we have 18 and then x. So what's the biggest thing that goes into 6, 9, and 18? 3. 3 goes into 6, 3 goes into 9, 3 goes into 18. Nothing larger than that. Yes, 6 goes into 6 and 18, but it doesn't go into 9 nicely. You get a remainder if you did it. So you need the biggest thing that goes into all of them nicely. So 3 is the option here. If this had been 12, then the GCF would be 6. That makes sense? So for us, it's going to be 3. And then one thing that becomes a little more challenging at first is for the variable portion. What power of x will go into all of them? We already know the answer is 3x. But you choose the smallest power that you see because the smallest power will be the one that goes into everything. X cubed goes into x cubed, but it doesn't go into x squared nicely. If I were to take x squared and divide it by x cubed, it wouldn't go into it nicely. I'd be left with the denominator x, which I don't want. X squared, it does go into x cubed. That's fine, but it doesn't go into x because you'd be left over with it. You'd have a leftover x in the denominator once again. So that's why it's going to be x. So GCF is equal to 3x. As you get better and better at this, you start not needing to worry. Now, these ones that I've done so far, these first ones, especially B and C, they've got multiple variables. That's going to kind of become a thing of the past for us for a little while. You're not really going to, this is just to kind of see how it works in action with weird stuff. But the first time you really will encounter multivariable stuff would be in Math 283. So it's mainly meant to kind of illustrate the point. But for us, most things are going to look like part A. So when I'm looking at it, what is the smallest number that goes into all of those? The largest number that goes into all of them? 5. Not 10. 10 does go into 40, but it doesn't go into 25 nicely. So the GCF, but we can definitely break it up. So 10k to the 6th, negative 25k cubed, and then a 40. And the 40 doesn't have a k. So as we said, a 5 is correct for the number portion of the GCF. What's the GCF of the variable portion? So that would be, I love the idea, yes, you're right if it was just this. If it was just that, then k cubed would be correct. But the issue is that technically speaking, there's a k to the 0 power here. There's a 0 power, which is equal to 1. So it's just going to be 1. So the GCF is just 5. Let's talk about that one more time as people are writing things down. So k cubed does go into k to the 6th, and it goes into k to the cube, to the 3rd power. But it doesn't go into 40 nicely because there's no k's. So you could write k to the 0, or you could just write 1 there and realize that the only thing that the largest number that goes into 1 is just 1. That's why the GCF there is 5. For part B, unless there's any questions on part A. Part B, I'm going to write it down, 8xy, and then 4xy squared. Yes, I know, I keep forgetting to charge you. So the number portion of the GCF will be 4, because 4 goes into 4 and it goes into 8. The GCF of the x portion would be x to the first power, and the GCF portion for the y would be y. Not y squared, but y, because it needs to go into everything nicely. So the GCF would be 4xy. Last but not least. And so you can do this little chart if you want to, or you can just kind of fill it in sequential steps. So that's what I'm going to do on this last one. I'm going to look at all the number portions. What's the GCF of the number portions? 9, because 9 goes into 9, 27, and 18. So the GCF will be 9. And then for the A's, take a second. Looking at all the A's, they all have A terms. They all have, sorry, A factors. A to the fourth, A to the third, and A to the second power. So what should be the GCF of the A portion? A squared, yes. And for the B portion, B cubed. Very, very good. That is our GCF. That's the way I normally do it. When I started off, I would do the chart. But as I got better, I just kind of do it in sequential steps. I just take care of it step by step and then work with it later. Any questions on that? Time, clock. And that's great and all, but how do we factor it out? Like finding what the GCF is great news. Cool, we got it. But how do we actually factor it out? So we're going to do an example on how to to see how it's done. So factor out the GCFs of the following polynomials. Notice that I'm not saying factor it completely. We'll get to that soon enough. But for now, we're just worrying about factoring out GCFs. We'll deal with factoring trinomials in a little bit. So step 1 is to identify the GCF. So for us, in this example, I'm going to do it in sequential order again. Take a second. I want you guys to jot it down. I want you guys to figure it out. I'll write down, we'll come together for the answer. Ready? No, still working. Okay. Thank you for letting me know. So I just love factoring and I get excited about it. So this brings me back to fond memories of Miss Arrington beating us with a ruler. So we got it. So we figured it out. Good old school. Good old K through 12 school. Back in my day. We had they were allowed to use rulers on us. No, I'm kidding. Miss Arrington was one of the sweetest women ever. Though she was a little bit strange. She ate a lemon. I remember being in class and we were just doing a worksheet and she just mumbled to herself and said, "I don't want this lemon to go to waste," and just started peeling a lemon and eating it raw. Just a lemon. Crazy behavior. That's skinwalker behavior right there. So, anyways, what do we get? 6x squared y is correct. I almost wrote 3 when I was looking at it first because I forgot that 6 goes into 18. I was just looking at 3 and 9 and I wasn't thinking about 6. So every once in a while, the good news is, by the way, if you don't factor out the true GCF, you can still factor again. There's not a problem. You might notice that there's more factorization that needs to be done. That's okay. So once you've identified the GCF, what you're going to do is you're going to factor it out by dividing all of the terms in the polynomial by it and putting it out front. So what that looks like in practice, and you start not having to write this step and to go immediately to the final part of this step, and I'll show you. But so we're going to put a 6x squared here, 6x squared y, excuse me. And then you've got 18x to the 4th y cubed divided by 6x squared y minus 30 x cubed y cubed divided by 6x squared y plus 12x squared y divided by 6x squared y. And if you've done this correctly, if you chose the correct GCF, you'll notice that all of those denominators, those red denominators, will go completely away. If they don't, that means you probably messed up. And that happens. That happens. So 6 goes into 18 3 times, and we get our final answer, our final answer, which will be 6x squared y. Don't forget about that out front. 6 goes into 18 3 times. X squared and the x fourth cancel slightly, and we left with an x squared. Y cubed and the y cancel slightly, we're left with a y squared. It's 30 divided by 6, that's 5. X cubed divided by x squared, that's x. Y cubed divided by y, that's y squared. And then last but not least, plus 2. And that is our answer. The x squareds will completely cancel, and so will the y's. So all we'll be left with is a 2. So that's what's mathematically going on, and I'll explain in just a moment. But ideally, what happens as you get better and better at this, and honestly, it's one of those things that when you get better at it, it actually becomes easier. Not just like exponentially easier. It's not like one of those things where it's just the same difficulty. Even if you get good at it, you're more efficient at it. It becomes faster. So what you'd like to get to is just doing these things in your head. Just work on each one separately. Think about this thing you've written down and then look at it and divide it by it in your head, if you can. Ideally, I'd like you to get to that point, but if you're still working on it right now, that's fine. And then step 3, which is optional, is to, of course, check your work, right? You can always just FOIL it out. But the one thing I did want to say is, why can I do that? That seems like kind of magic. I'm saying just put it out front and then divide each term. Why does that work? And the reason is that we're just cleverly multiplying by 1. We're doing that trick, the multiplicative identity. What we're doing is we're taking our original polynomial, 12x squared y plus 18. Oh, I wrote it in the wrong order. That's a typo. Not that it really matters. But x squared y. By multiplying it by 6x squared y over 6x squared y, what I'm doing is I'm really multiplying it like that's by multiplying by 1, so it doesn't change anything. And then furthermore, I'm realizing that as a fraction, I can write this as a multiplication of 2 different quote unquote fractions. One as 6x squared y over 1, and one as 1 over 6xy squared. And then what I'm doing is I'm distributing this into all 3 terms, hence why I get it in the denominator. That's why it's mathematically happening. Another explanation, that's what we do in practice, but what's really happening is you're breaking the each term into a 6x squared y and whatever's left, and then using the distributive property in reverse. That's what's actually happening, but in practice, this is what you're doing. So this is what I would recommend. Because the other way is not nearly as intuitive. But any questions on that? So identify it, then divide it out of each term. We're going to finish the GCF factoring, and then we'll take a break. So for this first one, part B, step 1 is to identify the GCF. I'm going to write down step 1, but if you want to not write that down, you're more than welcome to skip it. GCF. Take a second, identify it yourself. The more you practice this, the better you get at it. And it just feels good to do mental math, in my opinion. You're never like, it's a good brain exercise. It's like have you ever tried to do those, the classic one is the pat your head and rub your tummy, right? It's training your brain to think outside the box. There's one that I've loved to try and do. It's where you Like people watch the recording, you can't do this, but immediately switch. It's very hard to do, the switch between each hand, or doing this with this and then switching it like that. It's very, very hard to do, but it's a good brain activity just to keep your brain active. So GCS, what do we get? 12W squared is correct. So then step 2 would be to factor it out front. So we'll write 12W squared out front. And then this is what happens in practice. So I look at it and say, okay, what does 12? This is how I'm doing it in practice. In my head, I say, okay, how many times does 12 go into 36? 3 times. So I write a 3. And then how many times does W squared go into W? There's a remainder of a W. And then the second term, everything cancels out. But it's not going to be 0. It's just going to be a factor of 1. So minus 1. And there we have it. Any questions on that? And you can FOIL it, you can distribute it out and see that you get the exact same answer. Part C, go ahead and work through part C and part D. I will slowly fill in details. Trust you guys, I think you can do it. And if you have questions, feel free to ask. Oh, I forgot to do something. I forgot to mention something in step 2. I forgot to write it down. It's there, but I forgot to highlight it. If your leading term is negative, it's not required by any means. You'll get the same, like you will get full credit regardless of whether you do this or not. However, when it comes to factoring quadratics, it's much better to deal with a leading term that's positive. So I recommend if your leading term, your highest degree term is negative, factor out a negative version of your GCF. So for example, with part C and part D, the leading terms on both of them are negative. So find what the GCF is and factor out a negative version of it, which will change the sign on the insides. Maybe we'll do C together and then I'll let you guys do D. So the GCF of C two, yes. And then no X's because the last term doesn't have any X's, but all the terms have a common factor of Y. So GCF is 2Y, but since the leading term is negative, because leading term is negative. It's not required by any means, but I promise you it will be beneficial. You will thank yourself later if you get comfortable with factoring out negative GCFs if the leading term is negative. Leading term, by the way, as a reminder, the leading term is the highest degree term. First term is degree 3, second term is degree 2, and the third term is degree 1. So the leading term is the 4x squared y, the negative 4x squared. So we're going to tack on a -2, a negative sign in front. So when we factor out the negative GCF, this will be -2y. Now, because we're factoring out a negative, everything on the inside will change its sign. The first term was negative, now it's going to be positive. The second term was positive, now it's going to be negative. The third term was positive, now it's going to be negative. So when I divide 4x squared y by 2y, the 2 and the 4 cancel out slightly and give me a 2. The y goes away, but the x squared sticks around. The next term, write it down for yourself. You should get -4x because you take 8, divide by 2, you get 4. Cancel out the y, but you're factoring a negative version of your GCF, so it flips the sign. And last but not least, -3. And there we have it. Any questions on that? Give me a box. I'd like you guys to do the last one for all the kit and caboodle. But for most common thing that they all have. I deliberately chose this one for a reason. Excellent question. Excellent question. So JT asked, could we break the 25 into a 2 times a 12.5? And the answer is yes, you could. It's not wrong to do so. However, the reason why we typically avoid that is that we're going to try and factor that further later on. And when you start dealing with fraction or decimal coefficients, factoring becomes a little more of a daunting task. So it would not be wrong to do so. You could factor out a 2. In fact, the cool thing is, technically speaking, you could factor out whatever you want. I could factor out a 25 x squared if I wanted to. It would just lead me to have a bunch of fractions. The same process will work. I'll just have to divide every term by 25. The only difference is if it's not the GCF, then they won't cancel necessarily. So excellent question. Very, very good observation about the legal math. So you should get negative 1x squared. That 25 is being a butt, as my son would say. It's being a butt. Because all the other ones are divisible by 4. 36 is divisible by 4, the 8 is divisible by 4, 12 is divisible by 4, but that 25. And in order to be a GCF, it has to be able to go into all the terms, not just some of them. So we just get a negative x squared. So this thing, go ahead and factor it out now. Remember, that's going to change the sign of everything on the inside because you're factoring out a negative. Still working through it. Keep going through it. Once again, please remember, you don't need to be as fast as I am. I wouldn't expect you to be. Never let that get you down. Remember, I've been doing this for a long time. So you should get negative x squared out front, and then 36x to the 8th plus 8x to the 4th minus 12x plus 25. Any questions on that? When you divide powers of x, you cancel them. That's going back to, well, it's in the previous section, but if you have same base but different powers in the numerator and denominator, you take the top exponent minus the bottom exponent. So 10 minus 2, that's 8. And 6 minus 2, that's 4. 3 minus 2, that's 1. So 12x, and then x squared minus x, divided by x squared, they all go away. Any questions on that? Okay. So we're a little bit late on our break, but that's okay. Let's come back at 10:23. People watching the recording, go take a stretch. Do some guided meditation. Back to it. And so we've talked about how to factor GCS. Now let's talk about how to factor the rest of it. So factoring quadratics. So definition, first off, what is a quadratic? We haven't turned that terminology before. Well, a quadratic is a polynomial of degree 2. And therefore, so if it's degree 2, that means that its highest term is an x squared. So any quadratic can be written in the form ax squared plus bx plus c, where a, b, and c are in R. If you remember what that terminology is, just to save us on time, A, B, C, comma, that kind of E-looking thing means contained in or a part of, and then that boldface R means the real numbers. So it's saying where A, B, and C are real numbers. You can write that instead. You can say where A, B, and C are real numbers, but just if you want to use math notation, that's what you'd write. In particular, technically speaking, in order for it to be quadratic, then A can't be equal to 0, but that'll be a really stupid thing to do. So don't worry about that. It's A, B, C, and R. Now, I want us to be able to identify them because that's going to become crucial in how to factor. So identify the A, B, and C values. So with part A, what's the A value? 1, because it's a 1x squared. So I'll even write that down. There's an implied 1. Then B is going to be negative 16 and C will be 48. Part B is deliberately written in an obscure way. It's written not in descending form. And there's no BX term. So technically speaking, this is negative 5W squared. And it's technically plus 0W plus 47. There's no B term, hence the B coefficient would be 0. It's non-existent, and the only way that's possible is if it was 0, because 0 times anything becomes 0. And so A is going to be negative 5, B is going to be 0, and C will be 47. And by a similar argument to part B, part C, there's no constant term. So it's 0 as well. There's just an implied plus 0 here. So the A term, the A value is negative 33, the B value is negative 1, and the C value is 0. Any questions on that? Yes, JT.
How come on B you put 0W? Is it the same as if you put 0?
Well, I wanted to make it represent the W to the first power term, so I put a 0W. But you could just write 0, but the key thing is to understand that 0 is being attached to the BX term, or the B, the first power term.
Okay.
Is that all right?
Yeah.
Excellent question. All right. The first type of thing we will deal with are quadratics with a leading coefficient of 1. That is, A is equal to 1, meaning we're going to work with factoring things of the form x squared plus bx plus c. So no A term. And because it's the simplest case and these are the fastest ones to factor. Now, I want to kind of develop the process on why this works. So we're being remember to multiply binomials together, we use the FOIL method or the distribution method. That is, when we get x plus 3 times x minus 2, we FOIL it together. We get x squared minus 2x plus 3x minus 6, which can simplify down to x squared plus x minus 6. So our goal is to reverse this process. How do we go from x squared plus x minus 6 to x plus 3 times x minus 2? What can we do to figure that out? And so this is a very, very classic thing that mathematicians do. And I want you to know about it. There's I think I told you guys about a mathematician named George Polya, last name Polya. He wrote a book called How to Solve It. He's like one of the big names that you study in mathematics education. If you ever want to become a teacher and you take a course in mathematics education, you'll definitely hear his name because he developed several different techniques that all mathematicians use in some myriad of ways. Like maybe they're more prevalent, like they use one way more than the others. But one of the big things that you can do as a mathematician to try and figure something out is to work backwards to find an overarching theme. So what I'm going to do is I'm going to take care of a few distributions to figure out some type of a pattern. So if I had x plus, someone give me a number, 2, and then someone give me another number, minus 7. You know what's crazy is that's the exact fracture of one I chose. That's the exact one I chose. That's crazy. Those are pretty astronomical odds. But anyways, we FOIL it out. We get x squared minus 7x plus 2x minus 14, which then simplifies, of course, to x squared minus 5x minus 14. Okay. Do it again. Someone give me another number. 337? Sure. And then someone give me another number. Please say 1. There we go. Beautiful. So we'll get x squared plus x plus 337x plus 337, which simplifies to x squared plus 338x plus 337. So if we're looking for a pattern, if we're looking for things that become interesting here, notice that if the leading term is x squared, it always arises from an x plus or minus something times an x plus or minus something. So that means that when we're trying to factor quadratics of this form where the leading coefficient is 1, we definitely know that the first terms should, like the first term in each binomial part, the first term in each of these binomials should always be an x. That's nice. That's something to notice. The other thing I've noticed is that the constant term is always the product of the two constants in the binomial. 2 times -7, that's -14. 337 times +1, that's +337. So if we were to generalize this, like I was just picking 2 random examples, simplified, like specific examples to try and think something. Now let's make a general overarching discussion. So what if I did x plus or minus a blue box times x plus or minus a red triangle? So we distribute it out and we do that middle step. And at the end of the day, it would be x squared plus bx plus c, where the other thing I wanted to like, so I know something about c. C is going to be the product of the blue box and the red triangle, where C is equal to the blue box times the red triangle. Plus or minus, but we'll get to that. In generic terms. But then what I noticed, so how do I find B? Do you see any pattern with the B's? They get added together. We had 337, like our B term for the second example was 338. That's 337 plus 1. For the first example, we had -7 plus 2. That's where I got the -5. So where C is equal to blue box times triangle and B is equal to blue box plus triangle. So there is the trick. We need to find 2 numbers. So when we're in order to factor quadratics of the form x squared plus bx plus c, we need to find two numbers that multiply to c and add to b. If we find them, we have found the blue. Oh, let me write that down. If we find that, that means we found the blue box and the red triangle. The same 2 numbers need to multiply to C and add to B. If we find 2 numbers that do that, we found the binomial constants. We found the blue box and we found the red triangle, and that means we found the factorization. So if we can find the numbers that multiply to C and add to B, then we've got it. That's the goal. Does that make sense? Any questions on that? That's the reasoning behind it. We were looking at a specific example to make a generalization, a general argument on what to do. And this will always work. So as a little aside or a trick, it's you should always try and find the 2 numbers that multiply to C first, because there are only a handful of integers that do that, right? If C is 6, there are only 4 combinations: 1 and 6, 2 and 3, 3 and 2, 6 and 1. Right? There's only 4 combinations that work. But there are infinitely many integers that could add to B, because all you need to do is just add 1 to one of them and subtract 1 from the other term, and you find another pair, right? To add to 6, There is 7 and -1. There's 8 and -2. There's 9 and -3. There's 10 and -4. There are infinitely many pairs that work, but there's only a handful of pairs of integers that multiply to C. So it's always best to start with things that multiply to C and add, and then find the thing, and then verify if it adds to B. So to factor this one, I need the two numbers to multiply. The way I usually write is this. They need to multiply to +8, and they need to add to 6. So you can either jot them down in light pencil and see whether or not they work, or you can just put this on some scratch paper and do this multiple times until you finally get the right one that you want. So it takes practice, but it's all about just playing with the numbers to see what works. Does anybody see the factorization of 8 that will work? 4 and 2, because 2 plus 4 or 4 plus 2 doesn't matter. 4 plus 2 will equal 6. So the answer will be 4 and 2. That's my first proposed thing, and then I verify it in the adding, and it works out. It works out to be 4 plus 2. So that gives me the factorization right off the bat. I get x plus 4 times x plus 2. And I guarantee you, if you FOIL that out, if you distribute, you will get the exact same answer. You will get x squared plus 6x plus 8. And that's how you do it. You find the two numbers that multiply to C and then add to B. Part B we're going to do together because this one's an interesting case. The good news with part A was notice that the B term and the C term were positive. That actually limits our work because the only way to multiply to a positive number is if both things are positive or both things are negative, right? So, and since our B term is positive, it's a positive 6, we knew it couldn't be -4 and -2 because then that would give us a -6. We'll see it again here in this one. So w squared plus w minus 1. So we want two numbers that multiply to -30, and the same two numbers need to add to +1. Take a second to figure it out. You get better and better at this. This is the way I learned how to do it. Like we're learning it for the case where a equals 1, but this is what we call kind of the trial and error method. And this is the way I learned it. I didn't learn about the other methods until I was in grad school, honestly. It's just because my teacher just beat it into us. Ms. Arrington really made us do the guess and check method. But does anybody know the numbers? 6 and -5, right? Because we need to multiply to a -30. So one number needs to be positive and one number needs to be negative. Now, since our B term is positive, that means that the bigger number should be positive and the smaller number should be negative. But you'll start to notice these patterns as we go along. But +6 and -5, does that, like that multiplies to -30. Does it add to +1? Yes, it does. So that gives me my final answer, which is w plus 6 times w plus -5, which is really just w minus 5. Now you don't need to write this down, this next thing that I'm going to write, but so you just kind of finish what you're writing, and I'll be filling this in for a second. What happens if you say, well, you notice it, and you but the way your mind thinks of it, you write the -5 first, and so therefore you get w minus 5 times w plus 6. Who's right? They're the same. Remember, commutativity of multiplication. We've got one term times another term. You can flip it around however you see fit. So it doesn't matter which one you think of first. As long as it multiplies to C and adds to B, you're good. So it does not, commutativity ensures that they're the exact same thing. All right. We're going to do C together because C is an interesting case. And then I want you guys to do D and E by yourselves. So x squared plus x plus 1. So we need two numbers that multiply to 1, and the same two numbers need to add to 1. The only factors of 1 that I can think of are 1 and 1. But 1 plus 1 is 2. And then I'll say, well, maybe I can do -1 times -1. But -1 plus -1 is -2. So those are the only options, and none of them work. No options work. Does that mean this thing? So this is what we call a prime polynomial. So a polynomial that cannot be factored into binomial terms with quote unquote nice coefficients, i.e. rational things. So like fractions, but typically speaking, integers is sufficient. We call that a prime polynomial. So what we would write is we would just write this as prime. Now, what you may be wondering, and I think you should, is so does that mean it cannot factor? Does that mean it like there's no way to break it up into binomial terms, like a x plus something times x plus something else? And the answer is no, it can be factored. It just can't be factored nicely. It requires the usage of what we call the quadratic formula, which we'll talk about soon enough. But this thing will require you to work with irrational numbers and possibly complex numbers. So for example, if you see x squared plus 1, that is also a prime polynomial. You don't need to write this down, but x squared plus 1, there are no two numbers that multiply to 1, the constant, and add to 0. Multiply to +1 and add to 0. That's not possible. It's a prime polynomial. And this is why I love mathematics, and I feel like it is what makes us human. Honestly, like I could go on a huge rant about this. My wife and I have talked about it ad nauseum, but I feel like mathematics is what separates us from animals. You might say like language is and writing is what separates us, but writing legitimately, if you look back in early history, writing was only used to do math because it's really hard to do math in your head with big numbers. So legitimately, math like language was written so that like what language was created so that we could talk about mathematics. This is the thing that makes us human. So I like that. At least that's my opinion. And the reason why I bring that up is this is what mathematicians did. They saw this and said, well, there's no two real numbers that work. There's no numbers that work to do this. And then mathematicians said, but what if there was? What if there was a number that did this? And then all of complex numbers came about. This thing does factor. It factors to x plus I times x minus I, where I is equal to the square root of -1. I is what we call the imaginary number. It doesn't actually exist in the real world, but in math world, it does. And that's what mathematics is all about, is saying, well, what if I did this? What if it was true? What would happen then? And once they did this, all of complex numbers started to blossom. This happened in I think the 1700s. Specifically, there's a guy named Cauchy, Augustin Louisville Cauchy, and he has his name in every theorem of complex analysis. So cool thing for we won't really study complex numbers, sadly. It's just not part of the curriculum anymore. I think it should be, but that's neither here nor there. If you cannot find two numbers that work, it's going to be prime. If that is to show up on a quiz or an exam, I try not to because I feel like that's a cheap shot on an exam to have a prime polynomial. But if you try everything and nothing works, write down that it's prime, but put a dash next to it on the exam and come back to it. Start fresh, start anew, and try again. And if you really can't find anything, then it must be prime. Maybe if I do put one on, I'll say in the problem statement, like I'll like usually if it's a factoring problem, I'll say like factor the following polynomials like A, B, C, and D. And maybe I'll add in a stipulation. I'll write in italics, one of these polynomials is prime. How about that? So that you know that one of them is. That'll be nice. All right. If you haven't already started working on D and E, please go ahead and do so. I'm going to slowly fill in details. more and more and more you practice these things, the better you get at it, and the more little tricks and patterns that you start to know. I have the answers up here if you'd like to check your work, but if you're still working, keep trying to find them. You'll be a stronger mathematician if you keep running through them. The better you, as I said, the better you get at it, the more common factors you start to look for, and the better like things you start to figure out. But you can't learn it without doing practice. So it might be that you're really good at this at the start. That happens. And if so, kudos. Otherwise, it might be a situation where you just need to practice and start getting comfortable with your factors. Feel free to use your calculator, especially if it's a big number. Like there are a lot of factors of 254, a lot of numbers that multiply to 254. So feel free to use your calculator to find additional factors if you're running out of ideas. Like start doing 254 divided by 14. Does that make a nice number? If not, move on to the next number up and so on and so forth. So part D, I know that the two numbers need to multiply to 60, but add to negative 16. So I know they have to be negative numbers because otherwise it would like, they can't be one positive, one negative, because then it would multiply to negative 60. And they can't be two positive numbers because if they were both two positive numbers, then they would add to a positive number, but we need it to be equal to a negative number when it adds up together. So negative 10 and negative 6 are the choices, or negative 6 and negative 10, however you found it. It's cool either way. You'll either get m minus 10 times m minus 6 or vice versa. Look around. Similarly for 16, for part E, 7 and 9 seem to be the choices that work. And there should only ever be one. There will only ever be one. If you find two, there's a problem there. And the reason why is very, very cool. Very, very cool. But that will require us talking about functions. But we'll get there. We'll get there. Okay. So looking at the time, oh, we're perfectly out of time. That's excellent. We'll come back next time with factoring quadratics with any leading coefficient. And that's what we'll learn next time, how to factor those things in that situation. All right, guys. If you have any questions, feel free to ask. Otherwise, you guys have a great rest of your day, and I'll see you tomorrow.